In this video we look at a concept called center of mass, which isn't all that directly related to momentum, but it is an important concept to consider in any of our physical analyses. And so here are some examples of why it's important. If we think about projectile motion, we know that all projectiles follow parabolic paths, and if we imagine a person jumping off a diving board in a strange fashion like this, where they just keep themselves perfectly straight, then basically any point on their body will follow a parabolic path as we expect. But what about if they do a front flip dive thingy? Well, then not all parts of their body will follow a parabolic path. Their feet go from here to here to here to here and over to there and who knows what. So that is obviously not a parabolic path, but we can rescue the situation by saying, well, if we look at their center of mass, which is going to be somewhere in the middle of their torso here, that center of mass does still follow a parabolic path. And if you are in the air with no other forces acting on you and you're rotating, you will always rotate about your center of mass. So that's why your center of mass won't ever deviate from that parabolic motion. Another example, this doesn't apply just to projectiles. All of our physical analyses apply to the center of masses of objects. So here we have a wrench sliding on a low friction surface, so we would expect it to go at a constant velocity. Well, the end of the wrench here certainly is not following a straight line like we would expect from constant velocity motion. But if we take the center of mass of this wrench, which is located up near this end here, that center of mass does follow a straight line at a constant speed. So, hooray, physics isn't broken. It's just a little more complicated than we thought. To find the center of mass of an object, so the position of the center of mass, xcm, what you do in this example, there are two particles, and if we consider that our system, and we want to find the center of mass of that system, you take the location of each particle times the mass of each particle, and then you add that for however many particles there are, and then you're going to divide by the total mass of the system. So it's kind of like a weighted average, but you're also taking into account the location of the masses, and you can make the denominator just a capital M that stands for total mass here. Okay, so in this case, this is independent of the coordinate system. I mean that's going to change your answer, but the actual location is independent of the coordinate system. In this case, you might want to choose this n to be 0, and maybe this is going to be 2, and this is going to be 6. So if these have the same masses, then we know that the center of mass should be in the middle of the two. They're a distance 4 apart, so that's 2, so their center of mass should be 4 at a location of 4 relative to this that we called 0. Now if we called that 0 location, then this would have been 4 and it would have been here at 2. So it's relative to the origin you choose, but the actual location is going to be the same. In their example here, MA is greater than MB, and so the center of mass is going to be closer to MA here. Alright, let's look at a little bit more complex example. We now have 3 particles, or people that we are assuming are particles, located at different points along this thing called a boat, apparently. And we're going to ignore the mass of the boat in this situation, and we want to find the center of mass of these 3 people, assuming that they are roughly equal mass. So x center of mass is the location. We're going to have the mass of one of them, and we can just call it m because we're not given the mass, and you can probably guess what's going to happen. Things are going to cancel out, times the location of the first mass, which is 1, plus m times the location of the second mass, which is 5, plus m times the location of the last mass, which is 6, and then we're going to divide that by the total mass, which is going to be 3m. So all the m's go away, and so we've got 12 over 3, m over m, the m's go away, and so we get 4. Now this m here is meters, not masses, and so the center of mass would be located right there at 4, which we would expect it to be up closer to these two guys up here, right? Now if the boat was significantly heavy such that we had to take that into account, the way we deal with that is we would find the center. So say it looks like this thing's like 7 meters long. The center of that would be at 3.5, so about right here. And so you would consider all of the mass of that object as at that location, and so then you would add that into your equation. You'd say mass of boat times 3.5, and then you'd also have to add mass of boat here, right? Anyway, that's how that would adjust the situation. In this case, we would pull the center of mass back a little bit. All right, something a little bit more complicated. If we have a two-dimensional setup like this, where we have three objects not in a line, conceptually we know that the center of mass is going to be somewhere out over here. And this brings up a good point, that the center of mass, even of a solid object, isn't always located within the object. If you have some angled piece of metal shaped like this, the center of mass will be over here somewhere. If you have a donut, the center of mass is in the middle of the hole in the middle. If we want to calculate this actual location, given some information here, then you do it separately horizontally and separately vertically, and then you just get the x and y coordinates. So in this case, they all have masses of 2.5 kilograms, and then we have these distances here. So if I'm just looking at the center of mass in the x direction, then I could ignore any differences in vertical height. So essentially I treat MC as if it's right here on top of MB at the same horizontal location. So MA looks like it's at 0, so I'm going to have M times 0 for that one, plus 2M for the MB and the MC, times the distance, which is another 2. And then I'm going to divide that by the total mass, which is going to be 3M. And so we're going to have 4 over 3 for the x location, and that is meters. These m's canceled out. Not that we need that, that was 0 anyway. So that is the x location, 4/3 or 3 1/3. That's not right. I mean 1 1/3. Go away. 1 1/3. So a little bit further than halfway, so right there to correspond with the picture. Okay, for the vertical center of mass, this time we can treat these two as located at the same place vertically. So we're going to have 2 times those masses, and those are at a location of 0, so that's fine, plus this mass out here at a location of 1.5. We divide again by the total mass of 3, so we're going to get 1.5 over 3. Those m's cancel out, so we're going to get 0.5 meters in this case. That was meters as well, right? So if that's 1.5, it's about 1/3 of the way up, and so our center of mass is located right there. If we wanted to find, this actual distance here, our displacement vector to the center of mass, you could just do Pythagorean theorem with those, and away you go. Okay, now that's nice and easy if you just have a bunch of particles. If you have an actual object of some blobby shape like this one here, what you're going to have to do is you're going to break that up into tiny little chunks of mass, and then you need to take that chunk of mass times its location and then add them all up. And so if we take infinitesimal chunks, we're going to end up doing an integral. So this here is kind of like our m, that's an ugly m, but anyway, our m times x part here, and then we're just adding these all up, right? The summation of all of those m's at different locations. And then we again divide by the total mass here, but that's going to be constant, so we can pull that outside of the integral. And another concept, I'll go back to an example of actually doing an integral here in a minute, but sometimes you'll hear the term center of gravity as opposed to center of mass. Those, in most all situations, are going to be the exact same location. The only time they're not is if gravity varies over the distance of the object. So I guess if you have a huge object, the gravitational force could be different on different parts of the object. But most of the time, the center of mass and the center of gravity are going to be the same location for regular situations. Also, if we're going to do that integral for blob-like shapes like this, we would have to write an equation that describes the shapes of this object as a function of x and y, and that can be just not worth it a lot of the times. So in practice, you can experimentally find the center of mass or center of gravity of an object just by suspending it from two different points. So if you suspend it from this point here, gravity, you can treat it as acting on the center of mass, and so gravity is going to line up, that point where gravity is pulling is going to line up with this point. So the center of mass has to be somewhere along this line. And then if you hang it by the black point here, center of mass has to be somewhere along that line where it reaches an equilibrium. So then the center of gravity, or center of mass, is just going to be at the intersection of those two lines. So a lot of times it's just easier to experimentally determine the center of mass of an odd-shaped object. Alright, let's get back to integrals, because I know you guys were all sad that I didn't do one earlier. Let's do one where we know what we should come out with. So if we have a rod of uniform density, we know that the center of mass should be right at the center of that rod, but let's show how we can derive that using the integral. So x center of mass is going to be 1 over the total mass of that rod times the integral of x times dm. In the other one it had r's instead of x's. That's just expanding it into 3 dimensions, but usually you're just going to be dealing with 1 dimension here. Alright, now if we say that the mass of each little chunk is equal to the density of the rod, and we use lambda for linear density, so it's the mass per unit length, times the length of that little section, that's going to give us the mass. And so we can make that substitution here, and we can pull that lambda out because we're assuming it's constant. So we've got lambda over the total mass equals x times dx, because we had a lambda dx substituting in for our dm there. And so now we just have to take this integral and we're going to integrate along the entire length of the rod, so from 0 to L. So this works out to be lambda over m times x squared over 2, evaluated from 0 to L. So lambda over m, my m became small, sorry about that, L squared all over 2. Well, that didn't really give us what we were expecting. We were expecting to get L over 2, right? Well, we can look at the total mass of this rod. Well, the total mass is going to be the mass per unit length, lambda, times the total length of the rod, which is L. So if we substitute that in for this ugly m down here, we're going to have lambda over lambda L, that's an ugly lambda there, times L squared, it's an ugly L too, having a hard time. Alright, over 2, the lambdas go away, one of the L's go away, and we get what we expect, which is L over 2, the center of mass is right in the middle of the rod. Now if we want something a little more complicated, let's say that it is not uniformly dense, but that the density increases from a value of lambda naught over here, and it increases up to a value of 2 lambda naught over here. So it's twice as dense on this end as on that end, and we're assuming that it increases linearly across the rod. So in that case, we need to write lambda as a function of x, and some of you can probably just kind of intuitively figure out what that linear function needs to be, but if not, just start out with a generic linear function. So lambda is going to be ax plus b, and then think about what the values have to be at these endpoints here and plug those in. So lambda of 0, which is going to be b, has got to equal lambda naught, so b is lambda naught, good. And then lambda at at L, which is going to give you a times L plus b, which we just found out was lambda naught. That we said has got to equal 2 lambda naught. So now we can solve for a. That lambda goes over there, and then you divide the L over, and so you get a equals lambda naught over L, so that makes our equation for lambda lambda naught over L times x plus lambda naught. So there is that, and that's just the start. Here comes the rest of the fun. So we're going to use that same equation, that the center of mass is going to be 1 over the mass times the integral of x dm. And then we're going to make that same substitution, that dm equals lambda dx. So we substitute that in, but now lambda is this thing here. So we've got 1 over m times the integral of x. And it's not constant, right? This is a function of x there. So we're going to have lambda naught over L times x plus lambda naught, because this whole thing here was lambda. And that is times dx. So we're going to have to integrate this thing. We've got 1 over m. We can actually pull out that lambda naught because it's in each term, and that is constant. So throw that on top there. And then we're going to integrate again from 0 to L, and we're going to start out with x squared over L plus 1, because we just got rid of that lambda naught, and all of that is integrated with respect to x. So there's our integral. I'm going to jump way back over here. So we've got lambda naught over m, became small again. This becomes x cubed over 3L plus x, and that is going to be evaluated from 0 to L. So moving right along, that x cubed becomes an L cubed, and then you can get rid of that L, so you've got L squared here over 3 plus this guy becomes an L. Oh, I screwed up, didn't I? I was thinking there was a problem there. I forgot to distribute that x over here. So instead of a 1, that should have been an x. This makes life better. Okay, so this becomes an x squared over 2. And we're back in business. So we're plugging in that L, and we get an L squared over 2 here. And that's good because we want to be able to add these terms. So 1/3 and a half, so that's 2/6 and 3/6, so that's 5/6. So we've got 5/6 lambda naught over m times L squared. Now we need to do that same trick of substituting in for m here to see if we can get things to cancel out, so we can get the center of mass just in terms of L, the location of the center of mass. But unfortunately, finding m is not going to be so easy as last time, because it is still lambda times L, but lambda isn't constant anymore. So we actually have to integrate. The total mass is going to be the sum of all the little masses. Okay, so this is going to give us our total mass now. And we can substitute in this same expression here, where lambda is this guy, lambda naught over L x plus lambda naught. So all of that is our lambda times dx, and we're going to integrate that also from 0 to L because we want the total mass of the rod. And we can go ahead and evaluate this integral. We can pull out a lambda naught again. We can't pull out the L because that guy doesn't have one. So we get x squared all over 2L. Now this really was a 1 when we pulled that out, so that becomes an x. And this is evaluated from 0 to L. And that gives us lambda naught L squared. That L is going to cancel, so we're just going to get L over 2 plus L, all of that. And so this is going to become 3/2 lambda times L. Plug that sucker in here for m. So we've got 5/6 lambda naught times L squared over 3/2 lambda naught over L, and we are almost there. The lambda naughts go away, one of the L's go away. Multiply that 2 by the 5, so you get 10/18 L, which is going to be 5/9 L. There you go. Center of mass of this guy with linear density, not not uniform density. It's going to be slightly towards this end, which we would expect. That's the more dense, that's a heavier end, so it moves away from the middle of the rod just a little bit. Alright, you guys made it. That's all. See you next time.